2005, Google actually came up with an architecture to address this. The problem that Google had was that they needed to index the internet, right? Google's a search engine, and one of the key benefits, or one of the key chidushim that Google had, was if you want to rank pages, you don't only have to understand what's on the page, but let's see what's popular on the page. Right? So is this page a popular page? So if I'm going to be searching for a page on butterflies, right, so I'm most likely going to want to go to the page, pointers out to other pages, so you can click on other pages, but you have no idea who's looking at you. So in order to understand who's looking at you, you have to be able to look at every single page, figure out who everybody's pointing to, and then kind of turn that around and say, okay, I'm being pointed to by how many pages, right? And so I have to be able to read in the entire internet in a way, and be able to look at, run a program that says how many pages am I looking at, turn it around and say who's pointing to me, and add them up and see who's a popular page, right, by topic area. So came in 2004, MapReduce paper came out, and this was Google's way of handling large-scale data to make this something that they can do in a matter of hours as opposed to a matter of a month. So just before I get there, what inspired Google to do this? So this is a map. They have a MapReduce architecture and a MapReduce paradigm. So MapReduce actually came from the 1960s with Lisp. So I don't know if anybody's a Lisper here. So the idea of Lisp is you've got lists. And usually the first element of a list is a function, and all the other elements of the list are data. And if you wanted to find the beginning of a list, you have something called a car, is what they call it, and the rest of the list is a cutter. So the idea is, what happens if you're dealing with a lot of data and you want to run a function against a whole list of data all at the same time? So they had this, and so it wasn't clear what function you'd be running, so there's something called mapcar, which says take this function and make it the car of every single thing on this list. So let me give you an example of what that might be. So if you have a three-dimensional space and you have an X area, an X line, Y line, and Z line to define a point in 3 space, right? So the distance between the origin and the point is just the sum of the squares, and then you take the square root of that. So it's very easy formula. The thing is, if you got 3 numbers, X, Y, and Z, you want to apply the word, the function square to each element in this list. So it looks something like this: square of X, square of Y, square of Z. Add them all up and then take the square root. So that's the Lisp, sort of the pseudo-Lisp way of doing things. But notice what it did. It took a function and it applied it to many different pieces of data. And then when it applied that function to all the data, at the end of the day, it just added them all up. So there was a map step, and then there was a reduce step. The reduce was the adding, and then finally the square root of it. So the Hadoop architecture, or really at that time, before Hadoop is the public domain version of Google's MapReduce, really that version just created a whole architecture that enabled that on big data very easily. So let's look at a motivating problem. So I was talking about Google's problem of trying to index the internet and find out who is the most popular. That's not the only measure of what's that's not the only measure of when I type in some term, which page comes up, but it's a very significant factor and something that they need to do. So if I'm going to write a single program that's looking for all the pages I point to, and then they take that whole list and then turn it around and say, find all the pages that are being pointed to by other people and add them up, I could write a very simple program that has a double for list, for each source URL on the web, and then for each target URL, find the target URL and source list. It's not on the list, add it, and then finally just create that list and figure out who's being pointed to, and then add it up at the end. Now, it's going off the end, but this internal loop has n targets, and there might be lots of n targets, and then there might be m pages on the internet. So if you're going to understand how long this can take, there's something called big O of notation to describe the complexity of an algorithm. Complexity of an algorithm is really just a notation to enable people to say, how complex is this algorithm? You can't measure it because you have different platforms. You can't say how fast it's going to run, because if I get a faster computer, it'll run faster. But the measure is based, if I have a certain number of inputs and I have to do something to those inputs, how does the how does the processing time of the algorithm vary with the number of inputs? So here we have something that takes, let's say if there's n targets per page and there's maybe 10 to the 9th pages, the algorithm will run in O of m times m, or n to the 10 to the 10. A big number. It'll take a long time writing a simple algorithm to go through and calculate who am I pointing, who are all the pages pointing to, and then turn around and say, okay, I'm being pointed to by how many pages, add that all up and come up with some number. So Google said, this isn't viable, we can't do this, the internet is growing too quickly. So what they did was they came up with an interesting algorithm. Well, it's too bad you can't get the end of the page.
If you want, we could try messing with the resolution. Should we try?
Yeah, we could try, yeah.
All right, let's take a brief pause here and see if we can make this work. You can ask if there's any questions.
Well, any questions so far?
I mean, n is pretty small. How are you going to beat? Is there a way to beat big O m?
What's that?
Is there any way to beat big O of m? I mean,
No.
there's no way to do that.
No, I mean, so it's n times m, so, you know, it might be small, it might be a factor of 10, right?
Described as a very simple description of an algorithm.
Exactly.
Algorithms of magnitude.
Sure, many algorithms,
Complex than what we're analyzing.
yeah, many algorithms will go polynomial, and the worst are exponential, which can't really finish in any real amount of time if it's got a large number. So what Google, just conceptually what MapReduce does is it basically takes each, I'm just going to present it in this way, although it's a little bit more complex in real life, but imagine you can take each document on the web and run a simple program against it to do that inner loop. To say, okay, for this page, how many URLs am I pointing to for each page? So I might have 10 to the 9th documents, and each one has a mapper that actually runs that inner algorithm and says, for this page, I'm pointing to the URL A, URL B, URL C, the second page, URL A, URL B, whatever all the different algorithms are. And then, when I get all those results, I sort them by the target URL. So then I say, who's being pointed to? I'm pointed to page A is being pointed to by this, by this line, by this line, by this line. I pull them all together and sort them by the target URL. Then I create a list of those URLs, and I might add them up, right? And I do that for each sorted list. So there's this phase where I do a map, create a list of output results, resort them, reshuffle them, and then do a reduce to be able to add up how many people are pointing to me. And at the end of the day, I'll have some index. So for each web page, how many people are pointing to me? Notice that I'm just running lots of algorithms in parallel. But as it turns out, running lots of algorithms in parallel is actually quite faster than running a single algorithm on a single machine. So in order to write this algorithm, the assumption is that you have this MapReduce architecture that enables you, that runs and sets all of this up, sets up the data, sets up all the processors, sets up everything I need. I don't have to touch it. All I have to do is write a very simple code as the mapper. I can say for each target URL, emit the target URL in the source, and it's really almost as simple as that. This is pseudocode, but it's close enough. And then the reduce step would be, okay, for each target URL, I just do, for each element in the source, add one for each pointing URL. So I know how many of those URLs are pointing to me. And it's really, this is pseudocode, but it's almost that simple. So instead of having to manage huge amounts of multiple machines that are running many different algorithms and coordinating them in parallel, the system does that for me. The MapReduce architecture does that for me, and I write very simple programs. And as it turns out, it's quite powerful. I can do these. I can run something that used to take a month in a matter of hours. And if I have parallel processing, often this is called embarrassingly parallel problems, because that inner loop that looks at each page and finds out who they're all pointing to, they're not dependent on each other. They can all be run in parallel. And if you got lots of machines, and often these architectures have up to thousands of machines, and they're having many processors running these things in parallel, you can get tremendous efficiency. So in reality, you're not, I can go through this in more detail, but all I'll say is you're not really saving anything in terms of order of magnitude of operation. It's still a complex algorithm. But what you're gaining is you're running all these many processors in parallel. So what used to take a long time on a single machine, you're just dividing. It's a divide and conquer type of application that runs on many different machines. So you can actually have lots of machines running in parallel and have that processing time be very much shorter.
Because it's separated out.
Separated each machine, and you can imagine that the entire web is kind of copied onto single, many disks, right? So you've got, maybe 1/100th of the web is on one disk, 100th of the web. I'm just making that number up, but you're just taking all that data and just spreading it across many disks, and you're running the mapper on that.
So the real trick behind it
Yeah.
is the fact that you're able to break it into smaller pieces that can be run individually, irrespective of all the others that have to be run.
Yes, and that's
really
that's one piece of the crux. The second crux is the intermediate results get shuffled. You can do
get ordered instead of having to flip it around.
right.
just
You can shuffle it. So it's a matter of like, it's taking them, spreading them apart, and then shuffling it to map and a reduced step. So algorithms that tend to be map and reduced steps that can be kind of boiled down to that it's very amenable to those types of algorithms. Here's another motivating problem, word count. So for example, in the area of understanding what web pages mean or what they're likely represent, well, nobody reads them all. You have to actually come up with an algorithm that tries to guess what these words, what this page is all about. So what you'd like to do is you'd like to count come on in. You'd like to be able to count all the words and determine which words are popular per page. This algorithm, all it's really doing here is says, it's, how many, for each document, create an array of different words in that document and count them up, right? And then do this across this corpus of documents. So if you want to summarize a whole corpus of documents, if you've got legal briefs, you might be able to figure out as legal briefs. If it's about biology, you might be able to figure that it's about biology. So how do you do this? By looking at the commonality, how many words show up in these documents. So you might notice the word like, if you're doing biology, you'll see biological terms show up a lot. And if you'll say, okay, this is probably something to do with biology, right? So this is just an algorithm in the process of all of that. But again, it's double loop. The middle loop is when you look at the number of words on each page and count them up. It's really independent of all the other pages. And then you sum them up at the end and say, okay, this body of text, what's this about? Is it about?
That's what Google has been doing for years. When they read your email and they presented ads, if you were discussing some legal issue with some friend of yours in your email, you suddenly saw ads from legal firms who dealt with exactly that which you got. You were discussing.
Yep.
And they were doing that 10 years ago.
Yep. No, this is, it's not, this is, comes from something maybe that happened, it was probably 20 years ago, where they determined there's cosine vectors is what they call them, how similar are two different documents. And what they'll do is they'll look at documents and sum up the words. So imagine you just have two words, and all your document has is two words.
And even in Yiddishkeit, you can be talking to someone about halacha, and they'll hit you with ads specifically, they know the long lists.
Yep, absolutely. So imagine all you had is like aardvark and elephant, right? And some documents had 20 times the number of words, used the word aardvark 20 times more than elephant, and the other one used elephant 20 times more than aardvark, right? So you can actually create a two-dimensional graph, elephant, aardvark, right? And kind of put a point over here, or for one document, a point over here for another document. Measure the angle between those and say they're pretty far away. Now you have a third document and say where does it fit? If this has elephant 13 times and aardvark only 7 times, it fits closer to this document than that document because the cosine measure is similar. So what they do is they take these words and they add them up and see, where does it fall sort of in the world of all these words. And you do this for many different documents. You have lots of different pointers. You find that documents sort of cluster around different sets of words, and you can find similarities those documents. But so that's just another example of these uses. So there's let's see. Yeah. Again, you go through the same steps. You read all the documents. You find each word. Here I have anteater and zoo, and aardvark and zoo coming from the second document. You do this for all the documents. You just iterate over all the words and just emit something that says document 1, aardvark, document anteater, document 2, zoo. And you can count up the number of words. And then as a result, you reshuffle them according to aardvark, according to anteater, etc. And you count how many documents have the word aardvark, or how many times those words appear in this entire document set. It's just another example of MapReduce. And here's the map algorithm. Again, very simple for each word in the text. For each document, emit the word plus 1. And then the reduce algorithm goes ahead and just says, now that I got all the aardvarks, I can count them up and count up how many aardvarks are and how many zoos there are. It's just another example of how you do MapReduce. Okay, so there's lots of different MapReduce programs written, distributed grep, so grep is just finding words and lots of text. Access frequency URL, graph traversal, not really well suited for MapReduce. You have to do multiple MapReduces if you're doing social network analysis, who's connected to who. If you go to LinkedIn and it says, so-and-so is 3 hops away from you, do you want to connect, So how does it know it's 3 hops away? You got a billion people on LinkedIn, so it has to do some in analytics to be able to walk the graph. And I don't know if they're using MapReduce or not. There's a reasonable chance that they are, but MapReduce, when you're doing graph traversal, takes a number of steps of MapReduce. You can only go out 2 steps at a time. Machine learning, as you were saying, classification, clustering. How do you find recommenders? So this is a good area for recommenders. Same thing when you go to Amazon and it says, hey, you might like this book. Well, how do you know I'd like this book? So it's part of machine learning that says there's a whole area of. They've got, in fact, so here's an example in Amazon. So they've got 1 billion customers, let's say, right? And they don't go through 1 billion customers. What they try to do is to find out who's like you, right? So they don't look at you versus 1 billion customers. They take 50 people or 100 people that are similar to you, and they found that because they've purchased a lot of the same things you've purchased, and they find out what they've purchased that you haven't purchased, and they say, you probably want this book. So their guess is either that either you want this item because the people like you like this item, or this item is similar to things you purchased in the past. There's 2 different types of recommender engines, but very similar to the email. So they'll look at it, analyze the words, and be able to compare it to other people's purchases.
It works remarkably well.
And it works remarkably well. They make a lot of money from that. And there's a library called Mahout where these are written in MapReduce to actually do these type of recommender engines.
They manage to do is, you look at it and say, maybe I do, want to talk to these guys because I am working, with these issues.
Yep, exactly.
They're right there.
Yep.
I don't want to say right on the money, but they're right on target.
That's their bread and butter. So there's just more MapReduce programs. So now I'm going to go into the architecture a little bit. So I talked about let's see, how much time? I don't think I'll keep you for the full 3 hours.
How long is your course?
I don't know. I'll try to. So this ends at 9? Is that it ends 9:30?
Well, we're here till midnight.
Okay, fine. Okay, let's see, conceptual architecture. So this is the original drawing of this architecture, where you have a user program that calls a master. You have a lot of data over here. You have certain workers over here, which run the map programs. There's this intermediate storage, and then there are reducers, and then produce results. All of these are on disks. Again, imagine lots of different racks, many different disks per rack, many different processors per rack, many different racks. So that's where the data resides. You're talking about they could live on petabytes of data. The first step is what it'll do is it'll shard the input files. It'll say, let's break them up. The input files are just key value pairs. Document 1, here's the document. Document 2, here's the document. Key value, key value. It breaks them into pieces and assigns workers. Typically, I guess, 16 megabytes to 64 megabytes per data size. So that's way bigger than standard blocks in a memory. They just decided we're just going to do, run for lots of data. We're reading it sequentially. It'll run fast. And so huge amounts of data are applied to each mapper or each worker over here. And it starts multiple copies of the program all at once and schedules them. That's all done behind the scenes. It does that for you. The architecture does that for you. And it handles multiple users generally. The second step is, the one copy of the program is the master. The rest are workers assigned by the master. So you have you're assigned a certain amount of mappers over here that run the tasks. It reads the input, creates temporary intermediate results. The reducers will come, it's partitioned into different regions over here according to how you want to sort it. You basically end up sorting these. And at the point when they're sorted, the reducers kick in. Reducers actually produce the results. And then, it's reduced at some point, and message is passed back to the master. It says, I'm done. And the output is now available for you to read. So let's see. I guess that's it. Here's another view of the MapReduce program. Imagine this is lots of different disk memory over here. I can't even read it from here, but you're reading it, shards it into pieces. Mappers read, blocks at a time. I guess that says something. That's just probably a mapper, some sorter over at this. This must be the result of the map. It's sorted, and then the reducers hit the sorted results, and now the results are placed again on a different file in the data, in the large. Okay. Okay.
Question. So if you do have a relational database, can you apply this somehow to data that's arranged in relational structure?
Yeah, the thing is that you don't have an automatic, you have to write all that. You don't have something that automatically sets that up for you. The MapReduce architecture actually is an operating system all on its own. So all you need to do is just create a master program. In the master program, you have the map and the reduce. It handles all the rest of the processing, all the scheduling, all the handling of the intermediate results, sorting, all done automatically. You would have to create that infrastructure in a relational database. But yeah, I mean, there's nothing inherently about that you can't do with relational data. The thing about relational data, however, is what I'll get into is that the underlying data structure is very complex in a relational database. Relational databases are made up of smaller blocks, usually B-tree indexes, take longer to read. Access time is much longer because things are internally sorted. If here nothing is sorted, it's just one blob of data that it can screen through sequentially. Relational databases are optimized for random access, which means that even if you're doing sequential access, even though you might read along a major key, which if you're reading along a B+ tree, you can actually look at the very leaves of those trees and just follow those blocks all the way through because you have pointers to the next block. You don't have to keep on running through the leaves, but still there's a lot of seek time per, the ratio of seek time.
The overhead.
There's overhead. Seek time per actual block of data is very big. Here, the seek time per block of data that you're reading is actually very small.
They also look at scale over, there are relational databases that scale with partitioning tables. But even if you partition the table, you can't necessarily tell the workers do the process on the thing that it's partitioned on and just give them the results. You'd have to be working through an SQL query to come around.
I'm sorry,
Even if you could partition the data,
Yeah.
you could partition a table over a bunch of machines,
right.
you'd have to be able to work what you want into an SQL query, because you can't run arbitrary code on each of those machines and get...
Right, exactly, right, because that's, you essentially have to write rewrite the operating system to some extent.
So this relies not only on a DBMS, you actually have to have a customized operating system that's all set up for this
Yes.
I/O access.
Yeah, that's what the MapReduce architecture is. It is, in a sense, I can't say it's an operating system because they generally run on Unix systems, but in itself, it has its own structure. It has its own data structure, which I'll get to, and also it has its own infrastructure for processing.
You have thousands of machines too.
Yeah, my thousands of machines. Exactly.
And so Hadoop runs in that. Is the public domain tool that you can use
Exactly.
to do this.
Yes. Yep, exactly. One thing that you find, just sort of a last note before I actually go into further Hadoop specifically, is that you find that as if you're reading all the words, what you'll tend to do is you'll say, I found the word cat, okay, cat, comma, 1. Oh, I found another cat. I'll emit cat, comma, 1. You know, I found another cat. So you'll end up with lots of intermediate data if you're counting words, for example, right? So you have a lot of intermediate data. It takes up a lot of time, and it also means that the reduce process is going to go slower because it has to just address a huge amount of data. So there's this mini reduce step that happens just after the map before the data is sorted, which is called a combiner. Usually the combiner is almost exactly what the reducer is. And it says, you know, the reducer will say, okay, take all the cats and add them all up. So you might actually do that at the combiner level just after the mapper. Say, okay, I've got 3 cats from this document. Let's just emit cat, comma 3. I've got 7 cats from this document, cat, comma 7. It just reduces the intermediate data size to some extent and makes it a little bit more computationally efficient. You can't do that for all types of data. You have to know what the operations are. So for example, you can't do that for something called average. So if your reducer took an average of something and you were taking the average ages of people, right? So let's say you read 100 people over here and their average age was 50, and in this other place you had one record that had an age of 10. You can't take the average of 50 plus 10 and say, oh, the average age is 30, because that, it doesn't make sense, because you see, you have to be very careful.
If you omit a pair, you could do it.
What's that?
If you omit a pair, you could do it, just do average and add.
You have to say how many, so you can say the average is for 25, elements or something like that. You have to be a little clever of how you do that. But yeah, so all I'm just saying is that a combiner works often, could be somewhat efficient, but you just have to keep in mind what you can use as a combiner, what you can't. Okay, so it's just an example of map has a combiner step before it actually does the shuffle and sort. Okay, so the next topic's really the Hadoop architecture. I'll go over this a little quicker. So it's a large-scale distributed batch processing structure, and it's able to scale to terabytes easily, petabytes, and maybe even beyond. I think they're talking about exabytes. I'm not sure who handles exabytes quite efficiently. So it turns out the Hadoop architecture, as it was originally set up, can't really scale to that. There's a new infrastructure called Yarn right now, which actually somewhat more scalable and somewhat more general than MapReduce. Let's see. What's that?
What's the smallest size that it would make sense to use something like this?
Yeah, I wouldn't do things less than terabytes because of the overhead. It's just relational databases, not using MapReduce, using whatever algorithms you would have. Under a terabyte, relational databases might go much faster. But once you start getting much larger, it really depends on the database. I'm not sure. I imagine Oracle might be much bigger than some other database, but I don't really know. I don't have any figures on how fast SQL Server or Oracle runs, per versus Hadoop, where that breakdown is. In general, when you're doing large-scale parallel. Yeah.
From what I understand over here is that if you have very structured data, then I can hear saying that a relational database could be more efficient.
So here's
unstructured data.
So,
there's no way.
So what I've been showing here was pretty much unstructured data so far.
Right, that's what I'm saying. I see there's a significant difference.
There are systems called HBase, public domain, Accumulo, which is actually public domain, but it was created by NSA and made public domain. And they're similar, but there's some major differences between the two, which puts a structure on top of this unstructured environment. And if you're clever enough about how you actually structure your structured Accumulo or HBase data, you can actually screen faster than relational databases at a large scale. It really depends on, you have to know the types of queries coming in. you sort of have to know that in relational databases anyway, because that's how you structure your indices. But in general, relational databases for oddball queries, things that you don't expect, might actually run faster than a cumulo because, or HBase, because if you really don't have index or structure, it's really slow, as opposed to relational databases might be somewhat slow if you didn't expect to create that index. In general, when you're dealing with parallel processing is a hard problem. Hadoop is a very specific architecture that takes care of a lot of these problems. I'm just going to cover some of the problems really quickly. There's this architecture called MPI, Message Passing Interface, which is used for high-performance computing. And that was pretty much the gold standard for high-performance computing up until Hadoop came along, basically, or MapReduce architecture came along. But it was used for large-scale physics experiments, and it was a programming language environment where you could have 1,000 different computer systems, and they all talk to each other, each one doing separate things. However, you pass messages and say, okay, I'm done with my little part of the simulation of some atomic explosion or something like that. I'm passing my results to you, and you do your part, and you set the state now to something else, and then you could have like hundreds or thousands of these different processors running, doing different things. And it's very complex, number one, just to keep that all straight, to write software to do it, to keep that all straight in a normal operational environment. But what happens when processors fail? And that's going to happen.
If you're allowing for that in your algorithm, it's no big deal.
Well, but you have to, in MPI, you have to manage that.
Understood, it's managed,
But
Star went offline.
Yeah, but it turns out it is a big deal. It's not a trivial thing, because sometimes you're depending on somebody else's result, and at some point that guy fails. I have to kind of roll back many transactions, and when you're dealing with complex interrelated processes that actually have to talk to each other, and that their results are based on other processes, at some point you realize this isn't, we have to kind of roll this back. There's a lot of state to be rolled back, and it takes a lot of bookkeeping to understand where you've got to roll it back to. So it does take some significant managing. You have to deal, even just in an environment, you need multiple software versions, you have a lot of different systems, keeping 1,000 different platforms up to the same version of Unix or whatever you're using. It's not such an easy problem. It's not technically a hard problem, but it's just managing it becomes hard. Networks, there could be partial failures in networks, meaning that you have to find different routes to pass messages around. You can run into network congestion. You have to balance the load. I mean, that's all doing that, and you're writing a program to manage multiple processors. Just conceptually, keeping all those processors and what they're doing straight is hard enough. But then again, managing the load and deciding, gee, this processor is kind of busy. I got to have a duplicate running something else, running in parallel, and pull the results together. Or maybe I have to route my data a different path now because there's congestion along this piece of the network. That becomes a major network. That becomes a major nightmare. Memory. What happens when disks crash? Right? This disk space may be low. You need to kind of fail over into other disks. Data could be corrupted. How do you deal with corrupted data? You can have, if you're dealing with transactional data and you have locks that you don't want somebody to mess with some piece of data until some process is finished, and if the lock fails, or if the lock is not released, and you have processors just waiting there forever, how do you deal with processors unlocking? Or resource contention, deadlocks. They're both looking for the same resource, and then you have to deal with sort of localized deadlocks, pull that apart, and then roll all that back. There's a lot to deal with. Concurrency control and transactions, very hard problem. Just as a simple problem, if you have two machines, you want to transfer your money from your account in Bank 1 to your account in Bank 2. So you're going to be reading something from Bank 1, and then you're going to be depositing it in Bank 2, right? If it crashes somewhere in between, you don't want to be left with a situation that, gee, I don't have that money in Bank 1, but it never made it to Bank 2 either, I'm out, right?
The dollars are lost in the network.
Yeah, it's in the network, right. So real concurrency control manages that. Or let's say two people are writing, or one's reading and writing, and at the same time, you don't want people to clobber data, right? So it's very easy when you got one person, there are problems, but when you have many people that are reading and writing the same data, it's a significant problem to manage that. Recovery, Many databases, you deal with acid properties, so you have atomicity and durability. That's the part that deals with recovery. Whatever I do to the database actually stays there. Even if it just crashes, the next time that disk comes up, it better be there, right? So that there's a lot of overhead in making sure that happens. The concurrency control deals with consistency, meaning that that whatever I do, the database ends up in a consistent state. Not very easy when you get multiple people banging on lots of data. And also isolation, that it actually runs as if I'm the only user on the system. Concurrency control handles that. There's a lot of techniques and there's a lot of overhead in relational databases that deal with that. If you're dealing with large-scale, massive systems, MPI, message passing interface, that you have to manage all this, it becomes a nightmare. It's really untenable. It's not scalable. And security, I don't know very much about security. You're the guy, right? Security is a major issue all in its own right. So, so how do you deal with that? Let's see, processor, let's see, we're dealing with cost-based operation. And I'm just talking about managing it. What happens if you've got multiple ways to evaluate the system, evaluate your algorithms, and there's a lot of different ways you can lay out the processes on multiple algorithms and have results, intermediate results, be shipped from place to place. You want to do that in the most optimal way. If you're dealing with, so managing that is a very non-trivial problem. So I'm just going to skip this for a while. So Hadoop just kind of takes, just undoes all of that. It's got a very specialized process. It can't be as general as MPI, message passing interface. But what it does is it runs all these mappers in parallel. And all it says is, if one fails, just start it again. That's all, right? They don't talk to each other. There's no interaction. There's no data passing. They all just write their results to intermediate memory. And when they're all been written, then the master wakes up the reducers and say, okay, they've all been written, now reducers start. If one of the mappers stops, says, okay, I haven't heard from you in a while, let me just restart it, right? And that's all it does. It simplifies the architecture significantly. You can't be as general and complex as you have in this general large-scale distributed large processing system, but for what it does, it doesn't really care. It's just two steps, map and reduce. Yeah?
If there's a catastrophic failure where it can't be restarted, what examples more of these also using reps?
So what it does, when I get to it, I'm almost there actually. There's an underlying data system which uses duplication significantly. So for example, catastrophic failure, this processor went down, my data went down with it, can't do anything about it, it's gone, right? But generally, you can actually create as many different duplicates of that data across your system, and it's managed. The manager knows where all these data lives. Typically, what it does is it'll keep a copy on the same rack, so that if one processor goes down, it can actually go to some other processor on that rack. And typically it has another copy on a different rack in case that entire rack goes down. You can still find that data file somewhere else.
And that's all built into this?
All built in, yeah. Let's see. Yeah, so it uses replication. So it's really simple. They just all run in parallel. They don't talk to each other. And they all just have to finish. And when there is a little bit of a delay waiting for the last mapper to finish, perhaps, but when it finishes, it's done. No communication, we're on to the next step. And we can restart anything we need to. I think this is just what I said. As I said, node failures started, addressed by restarting tasks. Programs don't communicate with each other. There's no rollbacks. There's no concurrency control. Anyway, Hadoop processing is not a transactional system. It's not generally used as a transactional system. So you don't have to worry about ACID properties in general. Okay. It's supposed to be linear scaling. Little work is required to scale up. If you want to add a new processor, just plug it in. The Hadoop environment just knows how to deal with it. If you want to add a new rack, just plug it in, and it just knows how to deal with it. So there's very little you have to deal with. As you asked before, the overhead of Hadoop may be too small, maybe too much for small amounts of data. So just because of the overhead, you don't want to run this on small data. It's generally better to run it on a relational database until it gets up to terabyte to petabyte
You're not
level.
going to be running this at home.
No, you won't be running it at home. You could run it at home just for fun, but it's not computationally efficient.
Computers.
Right, I'm just saying.
Depends what you have at home also.
What's it?
Depends what you have at home.
It depends what you have at home.
Yeah.
That's right.
But you collect all computers that barely work and you get enough of them.
Yep.
They're not going to be
Electricity
fast
will.
Typically,
They're not
you
gonna
can
be
do this
fast
on
enough to
Amazon,
go to useful
you know,
work.
Amazon Web Services. Can you?
You can do this, yeah, you can get a Hadoop. You can rent some time, and they provide it. Yep. You can do this on Amazon. You can actually download Hadoop onto your own machine, just one machine, set it in one machine mode, and you can write programs on it and just kind of play with it and see how it works. You know, it's just it's not necessarily computationally efficient, but it's fun. You can develop your own. Yeah.
How does data get loaded into this?
Uh,
What does it look like on disk?
Well, I'm going to get to HDFS, but how does it get loaded? Actually, that's more of an art than an actual skill. So data gets loaded usually. It depends where the data is coming from. So if you're pulling sales records in or something like that, typically you have streaming interfaces and parallel interfaces that read raw data and write it out into the data structure, which is called HDFS, Hadoop Data File Structure System. And there are HDFS calls which actually will take that data, stream it in, and place it on the right disks, the right places. That's a bit of an art. You know, how do you get all that data in? It's run in parallel, and it's actually encoded and it's compressed, and it's done automatically as well. You can pick your compression scheme. There's like 5 available that you can pick from, and there's certain encoding schemes that you can pick from. And you read it out automatically, so it saves a lot of space. It makes it fast reading and writing, but you use HDFS calls.
Is data loading real time and while you're still doing things?
Yeah,
And it knows that it's ignore the new data until.
yeah. It's as I said, it's an art. It's not. Yeah, but it does occur in real time. Yeah. Do you have a question? Oh, okay.
Does it lend itself to being applied to an existing, shall we say, database? And I don't mean database in the classic sense, but database set of data.
You have to convert that to HDFS. So you cannot just read. You cannot stick it on top of a database system as it is right now.
I didn't mean database. I just meant your data store, your disks, if it knows what the organization is.
You have to restructure it. It's its own, which I'm going to get up to next. So it's not NFS. It's not NFS files. And the reason, which is, let's see, here we go. Hadoop Data Distributed File System. I'm close to finished. So basically, HDFS is really, it's called a distributed file system. It's designed for petabytes of data. It's designed for files that are bigger than any single disk. Right? NFS works on a single disk system. You have a namespace for the files on your disk. There's this database. There's this name server. Just this HDFS that kind of sits above your disks and can write large-scale files across many disks. Have one single file that stripes across many disks. NFS is network file system. It's almost all pretty universal, and the data structures we use right now, the files we use right now, almost all NFS on your Unix system, on your Windows system. So it's network file system, I think, is what it's called. Just a very common standard in files. But that means that you have on one system, you have many files that it manages all in one disk. So this is bigger than NFS can handle. What it does, it takes big chunks of data and just kind of writes them out all at one time. It's almost memory copy. The expectation is that there's going to be sequential access. Your map and your reducers are going to read these in order. So it can just read in big chunks of data at a time. There's no random access. Random access would be really bad because you're taking big file, and you have to find things in that file with no indexing system. But here, if you just assume I'm just looking at key value pairs and I'm operating on them, I don't care. It's just sequential access, and HDFS enables you to read these files very quickly. It minimizes the amount of seek time to the actual read time. Huge amounts of data for very little seek. So it's optimized for that kind of access. But HDFS would not be very good for random access. HDFS block sizes are huge. So, default Unix block size is way small compared, it's like 64 megs. What did I say here? Did I make a mistake? Yeah, typically they're like a half a megabyte, as opposed to 64 megabytes, so they're just huge. And it's not meant for random access. It's just meant for just sucking in lots of data at one time and processing them sequentially. The memory abstraction is a block. It's not a file, right? That the block sizes can exceed the size of any disk that you have. And they're just blocks are just easy to, you just do mallocs, you just can allocate space. You can kind of copy huge amounts of space. Replication is easy. Just copy from byte 0 to byte, whatever, 1 petabyte, and copy it somewhere else. And failure is just, okay, this chunk of memory is gone, I'll just rewrite it. HDFS has name nodes which manage the names on different disks, different racks, so you have different clients that manage these files, these data chunks within them. You have a single master, name node master, and you have a lot of slaves. Each slave typically deals with one of its processors. Files are split into more than one blocks. The blocks are stored as a set of data nodes. The name node kind of finds it, and the data nodes kind of retrieve it for your system. I'm just kind of pushing through really quickly. And there's a lot of load balancing that's done. Data chunks are automatically balanced so that you don't have a bunch ending up on one system. And that's part of the art of the ingest, making sure that the system is balanced, and it does do the balancing. And it tries to achieve an even distribution, within 10%. And it moves the blocks around to achieve the balance. Can do this while other jobs are running, and the administrator can kind of manage all this. So just in summary, 905, so MapReduce, I talked about the history and background. It's a different programming paradigm. It enables you to deal with large-scale data for certain types of application. Generally, when it's embarrassingly parallel, you can run map on lots of different data in parallel. Just take the results and reduce them, pull them together. When you have an algorithm of that type, this system manages very efficiently. It's only for big data. For little data, it's a huge amount of overhead and not really very useful. I shouldn't say not useful, it's just not computationally efficient, right. Hadoop is an architecture that supports MapReduce. That's the public domain version. It's on Apache. You can go get it, download it, run it on your own system. It can run. The Hadoop has a great architecture. You manage very little. You deal with the computational complexity. It deals with reliability for you. You could scale pretty automatically. And HDFS is the underlying data structure system that enables you to represent large files that can be much larger than a single disk. And so that's kind of my Hadoop in a nutshell, and MapReduce in a nutshell. Yeah?
You feel the need both for the massively parallel analysis plus random access. So does Hadoop or a similar technology?
So,
is there any indexing at all?
no. So what you would do is you would use something like, on top of that, you would use HBase, and HBase, which is also an Apache. It's a structured system. Or you can use a Cumulo, which actually stores things in terms of more than a key value pair. It's actually, it's not a triple store, it's a quintuple store, where you've got a key, you've got a column family, which kind of put like attributes together, got a column attribute, you have a security column, you have a date column, and then you have a value field. And you have a structure there, and those can represent your data, and you can also create that file, which goes across many different disks. You can actually have a corresponding file, which is your index, which points to various elements in this initial file. So it's also a quintuple store, your index, and you can create as many indices as you want. And if you want random access, they provide random access, which you can actually look things up very quickly on an index and find corresponding rows in your initial file. So it is managed from that perspective.
But Hadoop
So it's through, you wouldn't use it through Hadoop. There's a layer on top of Hadoop, HBase and Accumulo. I can describe that. It's a different system. There's lots of different calls there, and it's a totally different system, but it's supported by Hadoop. I can actually talk about that, but it'll take another hour probably. Any?
Are you done?
Yeah, I'm done.
I would like to, as one of the representatives from JetTech, I'd like to thank you for taking the time this evening. It's very interesting, and I hope people had a good time. I'd just like to give a shameless plug for JetTech. We're a group of people who are trying to help the community learn new things about information technology and help people find jobs in the information technology field. So we're passing around a sign-in sheet. If you could put your contact information on there, that would be very, very nice. And we periodically run these lectures or discussion groups or whatever you want to call them. And we'd love to have you come back again. Please feel free to share your contact information. And if you know of positions, let us know, because we can help people. We're in the shotgun business for helping IT people find jobs, so, among other things. Thank you very much.
Thank you. Thank you. Thanks very much.
No. You did a great job. And prepared. So just
Network.
introduce yourselves to each other.
Okay, you done good.
Yeah.
Thank you.
Thanks.
Camera's off.
It took a while to get all connected, but
Yeah.
we did it. Appreciate the help.
I really appreciate it.
Oh, my pleasure.
I hope you don't feel that
No, that's just all. I was, I heard,
You have no idea how many people asked me what this is about. I figured the show could have anything bigger than, the other time.
that's okay.
There's so many people I have emails,
So-
I have phone calls.
So I would say from a lessons learned perspective,
Yes.
I think we need to have titles that are pretty clear to the average person
Right.
and
Right,
descriptions.
maybe.
A little bit clearer. People came up to me saying, I don't understand what you're talking about. So, I didn't really know what to say.
I mean, you could talk about, one approach might be to say, what is big data?
Yeah.
And here's a tool to manipulate it, and here's an example of a real world like Google and how they do it.
Yeah.
And,
I think we would have gotten a lot. That's more. I think you're right.
Yeah.
So, but no one asked me.
Okay.
So, but that would be my recommendation. I think we have to try and make it simple for people who may not know. but-
Sean Leibovich comes from Paul Weinstein.
I'm
Nice to meet you.
certainly
Yossi
interested. I didn't know
Leibovich.
anything about this
Leibovich.
stuff, so
From where?
I was very
I've been living here for about 3.5 years.
I appreciate the interaction.
Before that, you're
Great. It
fine.
was very
Okay,
nice.
and what's your in
Very nice to have you
want to
here.
go into
I
IT?
really-
So
very
I
much
started doing cybersecurity,
Okay.
but I chose that as the major, but
Okay,
I'm
good.
not
Take care.
Okay, nice to see
positive
you.
that's exactly what I want to do.
Thank you very much. I really appreciate it. So you're in school now?
Yeah,
Where?
UMUC online.
Okay. What time?
What?
I forget. Yosef,
Yosef.
right? Yosef Leibovich is studying cybersecurity at
Oh.
UMUC.
Very nice. I'm in the field.
Really,
Been doing it for a long time. Got a lot of gray hair from it. Yeah, that's Lata.
Amazing.
Do you have any contact information? I can give you a card if you'd like. It's nice to help other people.
sure.
If I can. I'm specifically doing an application.
He's on a different level.
What is the
You know, it's still in this push of the rate, but all of this is push of the rate.
That would be like
Right.
software development.
Did you learn it?
Yeah.
Okay, good.
No, I just, we get the, I now have the concept, what goes on. It has to be reorganized. You can't, what I mean by database, I mean, let's say CMS wants to take all the stuff that they have across their disks and just visit it and analyze it.
So what have you been doing?
You have to reorg the data. You have to read it in and put it in that
Right. They could probably use such a thing.